Hello students, in this video I'm gonna go over the unfinished business we had with continuous distributions. This should largely be revision from other units. So, and this is simply a list of very common distributions we're going to use many times during the unit. Obviously, it's not an exhaustive list. Okay, you know and love very well the normal distribution. Recall just that mu is a parameter, it's the mean, it can be anything, okay, so it takes values in the reals. Sigma is the standard deviation, needs to be positive. Careful that sigma square is then the variance of x. The density function is given here, should be fairly familiar. Now the CDF, it doesn't have a nice expression for this. It doesn't have a closed form expression, but often we're going to denote the CDF of a standard normal. Standard normal, of course, is a normal with mean 0, standard deviation 1. The CDF of a standard normal is often denoted here by the Greek letter, I believe this is phi or capital Phi, though don't quote me on this. Now, recall though that if x, so here x is a arbitrary normal variable, so with any mean and any variance. If you want a CDF of x, you can always express it using this the CDF of a standard normal. You just plug inside little x minus mu and divide by sigma. Well, if you want like an explanation for this, you can give a simple one. Probability that x is smaller than little x. Okay, this is just the same thing as big F of x. Well, you can rewrite this as the normalized x. Okay, x minus mu divided by sigma, but then on the other side you need the same thing. You need x minus mu divided by sigma. Okay, as usual, I struggle with my handwriting, but now you recognize that this thing here is of course just a standard normal. Okay, because well, that's a property of the normal. If you subtract the mean, you divide by standard deviation, you get to a standard normal. I suppose to be rigorous, this would need to be proven, but well, actually, yeah, technically this would need to be proven, but I'm pretty sure you've seen this before, that this thing is a normal 0, 1. Because that's the case, then you can write that this is phi of phi. So this is the CDF of a normal, standard normal, evaluated, of course, at this argument. Okay, so this is the same thing as saying this is phi of whatever this argument is, x minus mu divided by sigma. Okay, this is just the same thing as we have over here. Okay, the moment generating function, you have it here. It's always defined, so it exists for every possible t. Okay, and you know the shape, of course, of a standard normal. It has this totally symmetrical bell curve type of shape. The log normal, it's obviously related to the normal. Now, here we define it just without specifying the link with the normal. We just say this is the density, okay, and CDF. Okay, so x follows a log normal. Now, careful that x is then a strictly positive random variable. The parameters are the same, are defined in the same way as that of the normal. Mu is anything and sigma is positive. Now, this is just by definition the density of the log normal, so you can take it as given. If you want to derive the CDF, same thing, there's no nice closed form expression for it, but in those little calculations, we show that you actually don't need a new function. You can just use your old phi, which was the CDF of a standard normal, but inside you need to plug ln of x minus mu divided by sigma. Now let's just go over those calculations. The first line is just by definition. Obviously, the probability that the log normal is smaller than x, you just integrate the density from 0 to x. Okay, inside the inside bit here, this is just the density. Okay, so that's the same thing as over there. Now there's just a change of variable happening here. Okay, so we're going to make the change of variable ln y, whoops, ln y equals z. Okay, which also means that the derivative, well, d whoops. It also means that, you know, dz would be then derivative of this, so 1 over y dy. Okay, and that creates nice simplification because of course we then have y sorry, we then have dy is y dz. Okay, which means there's simplification over there. Dy, if you replace it by y dz, then this y here is going to cancel. You're going to get dz, and then everything else is the same. It's just that here, of course, we also have ln y, which is our z here, and careful with the bounds of the integral that change as well. When y is 0, then of course ln y, which is z, is minus infinity, and when y is x, then ln y is ln x. And then we're done, because then this, integrating from minus infinity to ln x, this density function, well, in fact, you recognize this. So you recognize this. This is the density of a normal. Okay, careful, a normal with parameters sigma and, sorry, reverse order, parameters mu and sigma, or sigma squared. Okay, so but it is evaluated at sorry, this is the density of a normal mu sigma. But then when you integrate from minus infinity to ln x, it means that you are getting the CDF of this density at ln x. Okay, so this thing is the probability that a normal mu sigma squared is smaller or equal to ln x. But because of the previous slide over here, this, you know that it's just phi of whatever the argument is minus mu divided by sigma. But here, careful, the argument is not x, it's ln x. ln x. Okay, so that's a nice way to get probabilities of the log normal using the CDF of a standard normal. Okay, now a little example having to do with the log normal. And actually, sometimes you might have seen that the log normal was actually defined in this way, but here we presented the densities, and then we want to prove this thing. If x is a log normal, show that y, a new variable y, which is ln of x, is itself a log normal. Okay, it's quite easy to prove. You start with y, so y is a function of x. Probability that y is smaller than any number here, little y. Well, this is, you just rewrite y as being ln of x. Then you can take the operation, you can take here the operation e to the, on this side, e to the ln x, and on this side, e to the y. You can do that because e to something is an increasing function. Okay, so you then get this, because of course e to the ln x is of course just x. But now that's nice because you know that x is a log normal, so you can just plug whatever we just saw over there, that the CDF of a log normal was this expression. So you use that, and you have that, careful. Here the argument, okay, you have the log normal. So this is the CDF of a log normal evaluated at this argument, okay, evaluated at e to the y. But remember that the CDF is the the phi evaluated at ln of the argument. But here the argument is EY. So then you have ln of EY. But ln of e to the y is, of course, just y. Now, look at this expression. Well, this is a CDF. This is a CDF of a normal mu sigma. Well, of course, as we saw a few slides ago. Okay, so it's a CDF of a normal mu sigma, and voila, you're done. Because the CDF uniquely identifies the distribution, because it's the CDF of a normal, you conclude y is a normal with those specific parameters, mu sigma squared. Okay, so the result is proven. Okay, again, if x is a log normal, ln of x is a normal. And of course, you could prove the kind of the opposite. Okay, you can do the calculation. I think I'm not going to do it, but you can do it easily. Show that if what do we want to show? If y is a normal mu sigma squared, then e to the y is log normal. Okay, the inverse operation is a log normal with those parameters, mu sigma squared. Okay, you can try to prove this using a similar method. Okay. Yeah. Okay, now just the moments here. Just a comment that there's a clever way to find all the moments of the log normal using this trick. Okay, if x is a log normal, then you know that x can be written as e to the y, where y, I'm going to rewrite it here just to make sure, where y in this expression, y is a normal, whoops, what problems with my my pen here. Y is, of course, a normal mu sigma squared. Okay, the y here. Okay, if x is a log normal with parameters mu and sigma squared, then automatically x and e to the y, where y is a normal mu sigma squared, have the same distribution. Okay, so it's just it's allowed to rewrite x as e to the y. Okay, but why do we do this? It's because if you look at this expression, expectation of e to the yk, well, that's actually just the MGF of the y evaluated at k, and we've already given the MGF of the normal. Is that expression, and so that's what you got. This is where this expression comes from. Okay, but here, so you know that the kth moment of e, of x to the k is given by this expression. Okay, and from this, so because k here, maybe we should have written k should be well, actually, k can be anything, right? K can be any positive or even negative, right? There's no restriction on k here for those manipulations to work. But in particular, if k is 1, then of course you fall back on the expectation, and then you can find the second moment, expectation of x to the 2, and from that you can deduce the variance. Now, comment, careful, you see, this we're still of course talking about a log normal with parameters mu and sigma. But in the case of the log normal, the expectation is not mu, okay, and the variance is not sigma squared, okay. The expectation is this more complicated expression that involves both mu and sigma squared, and the variance is this complicated expression that involves both mu and sigma squared. So careful with this. It's not because the parameters have the names mu and sigma that mu and sigma are the mean and variance, or the mean and standard deviation in the case of the log normal. Okay, this was true only for the normal. Okay, now okay, here I've written things previously, but I don't need them now. Okay, the rest is okay. Okay, now jumping to the exponential. Again, the exponential, you know it very well, so I don't think I have much to say here. Okay, the PDF is this. The CDF would be the integral of course, the PDF for x, so the integral up to x. Okay, it's not the especially hard integral. You get this expression that you're probably familiar with. The shape of the density is a kind of smoothly decreasing function. Okay, and again, I don't think I'm going to spend any time on this. You just have the expressions for the MGF. Expectation, I think you know that by now, but it's 1 over the parameter. The second one is 2 over the parameter square, and this yields that the variance is 1 over the parameter squared. And yeah, I mean, I think you know that the exponential is memoryless, but I think I might say a little something about this memoryless property a bit later. Memoryless, of course, means that the hazard rate is constant. But again, maybe later I'll say a few words about this. By later, I mean in a different lecture. Okay, now the gamma. The gamma has 2 parameters. Okay, here we call them alpha and lambda. Of course, those are just conventions. Elsewhere, you'll see that the parameters are named differently. This is just we need to deal with this. For us, alpha and lambda, both are positive. The PDF is given there. Just a comment that it involves this function I'm sure you've seen before. It is actually called the gamma function. Okay, the gamma function is a mathematical function. It's defined here. Okay, it's the integral of this. Okay, defined here for alpha bigger than 0. I believe there's ways to define the gamma function more generally for negative numbers and even complex numbers. But for this unit, we're not going to bother about this. We're not going to worry about this. We're just going to restrict to the case where the argument is positive. Okay, in which case that's the definition of the gamma function. And you also have those properties. Okay, okay, gamma 1 is 1. But then there's this very handy property that gamma alpha plus 1 is actually, you can obtain it iteratively from gamma of alpha. Okay, gamma of alpha times alpha is gamma of alpha plus 1. And those 2 properties together, they yield that if k is if the parameter is an integer, if k is an integer, then gamma of k is actually a very simplified or simple expression. It's just k minus 1 to the factorial. Or yeah, k minus 1 factorial. 2 the factorial doesn't mean anything. Okay, here just a plot that shows different shapes, but they're all gammas. So of course the gamma, because it has 2 parameters, there's a lot of freedom on how the density will look, because you have more to play with. Okay, this function is as a function of 2 parameters. If you play with the parameters, you'll get different shapes. Now to make the kind of the comparison of different densities, to make the comparison, I don't know, fair or comparable, we fix the mean to 1. Okay, so the expectation is 1 here for all those densities, but you see they have vastly different shapes. Okay, this one looks almost like this could actually be an exponential because the exponential is a special kind of case of the gamma, but the other ones, they look more and more like they start looking more symmetrical, even though they're all skewed. Okay, the important functions are there. As I said in class, you probably don't have to memorize those because they're in the formula sheet for the exam. But if you know them by memory, then maybe you save a few seconds in the exam. Just special cases. So the gamma is actually the more general version, in the sense that some distributions that have different names, they're actually special cases of the gamma with specific parameters. Okay, you probably know that the exponential is in fact a gamma in which the alpha parameter is 1. This can be seen easily but in the density. Okay, if you here for alpha equals 1, if you replace alpha by 1, you'll get x to the 0. That's going to be 1. So sorry, that's going to be 1. And then you're going to get lambda times e to the minus lambda, and then gamma of 1 is 1. So yes, you fall back on the density of an exponential. You also have that a chi-squared with v, or sorry, this is the Greek letter nu, I believe. I believe this is nu. this would be a gamma. This is in fact a gamma with nu divided by 2 for the alpha parameter and lambda fixed 1 off. I think maybe I should have said that nu here is integer, positive integer. Positive integer. Okay, 1, 2, 3, 4, etc. And lastly, maybe you've heard this before, a gamma alpha lambda, if alpha is actually an integer, okay, in the special case where, well, alpha is a positive integer, then this is also called the Erlang distribution. Okay, it has a different name in the specific case that alpha is an integer. Okay. Now I believe that's the last distribution in those slides. It's called the Pareto distribution. Now, just a comment that the Pareto distribution, maybe unfortunately, not unfortunately, but many distributions might be called Pareto. So there's many types of Pareto. So what we will call Pareto is the one that we present here. Sometimes it's called the Pareto type 2. Sometimes it's called the Pareto, the 2-parameter Pareto. Sometimes it's called the Lomax distribution. Okay, so here, if you follow this link, Wikipedia calls it Lomax distribution. But in any case, what we mean by Pareto is this. Again, there's 2 parameters. The names we give here are again alpha lambda. Again, those parameters need to be positive. The density is here. The CDF has actually a nice compact expression. Now a comment, the MGF does not exist. Okay, if you try to compute the MGF, you're going to get an integral, and the integral is going to be infinity. So then we say the MGF doesn't exist. I think we're going to see later that this reflects the fact that it's a heavy tail distribution, but more on that later. Okay, you have some formulas for the expectation and the second moment and the variance. Now, as a comment, the MGF doesn't exist. The expectation exists, but only for specific alphas. Okay, so if alpha is bigger than 1, then the expectation exists. Otherwise, if alpha is smaller than 1 or equal to 1, expectation is infinite. Okay, so you don't have any expression. Well, I mean, some people say the expectation is infinite. Some people say the expectation is undefined, right? But in any case, you don't have any expression. It's not a number, right? You might say it's infinity, or you might say it's undefined. Now, second moment, same thing. Okay, it's defined, but only for specific values of alpha. Okay, if alpha is smaller than or equal to 2, the variance and second moment don't exist. Okay, and just lastly, there's a plot here, shows you again, there's 2 parameters, so the shape can be quite different depending on the values of the parameters. Here, a few examples displayed for a Pareto always with mean of 1. And yeah, last comment, the Pareto really is like the kind of typical or very common heavy tail distribution. And heavy tail, we're going to come back to this concept later. Maybe you've seen it before. Roughly speaking, heavy tail distribution means that extreme outcomes, meaning outcomes that are very far away from the center of the distribution, from the mean or the median. So very extreme outcomes very far away from a central location of the distribution are somewhat likely. Okay, and again, somewhat likely, it's not very formal, but it means they can happen with some probability that's not that negligible. Okay, so and in terms of modeling risks, those are dangerous distributions. If a distribution is heavy tail, it means you need to worry about the fact that, okay, there's possibly very extreme outcomes that are going to happen. Okay, extreme losses or extreme financial loss or insurance claims. But we're going to come back to this concept of heavy tail distribution a bit later. Okay, I believe that's it for the summary of continuous distributions. If you have any questions about this, send them my way on the discussion forum. For now, I thank you for your attention, and I believe it's the end of the video. So bye-bye for now.